We are now going to move to our panel discussion. The panel is moderated by Gadi Singer. Gadi has had an illustrious career at Intel for close to 4 decades. He has made numerous contributions to Intel's computer architecture, hardware, software, and recently on AI technologies. Gadi is currently Vice President at Intel Labs, where he leads the Cognitive Systems Research Team. His lab pursues the emergence of knowledge-based cognitive AI as the next wave of human-inspired machine intelligence. Welcome, Gadi. The floor is now yours.
Thank you, Vasudev, and greetings to our panelists and all of you tuning in to this session. We have with us 4 leading researchers and thought leaders to discuss the panel theme, knowledge meets neural networks, both opportunities and challenges. And I would like to thank them for joining us for this discussion. Our panelists have previously laid out their views in position papers on what the future of AI should be, setting forth a vision of neuro-symbolic and hybrid systems. They are engaged in cutting-edge research on constructing systems leveraging both structured knowledge and state-of-the-art deep learning. I look forward to learning from them if they see knowledge injection as just one of many tools in the AI toolbox, or maybe as a major direction driving new level of capabilities in AI. And we will start with 3-minute opening statements, beginning with Gary. And Gary Marcus, hi, is a professor of psychology and neuroscience at NYU, and the founder and CEO of Robust.ai. Previously, he was the CEO and founder of Geometric Intelligence and director of Uber AI Labs. His research focuses on language, computation, artificial intelligence, and cognitive development. Gary.
Hey there. I was going to show a slide and I forgot to get it ready. I guess my opening statement is that there was inspired partly by the last talk and the last few minutes of the previous talk, is there's been a long-standing debate about symbolic manipulation versus neural networks. And I think that people of my generation thought that this was an important debate, and people of the new generation are mostly unaware of this debate, I think. And it's interesting to see things are sort of being reinvented to a certain extent. So the question was never, can you build a symbol manipulating system out of neural networks, but rather, do you want to? So there was a debate about whether we want to borrow in our cognitive architectures anything from classical symbolic systems. And there was famous PDP Bibles in 1986 by Rumelhart, McClellan, Hinton, and so forth. And they said, well, we don't think symbol manipulation is of the essence of human cognition. And then the debate was about cognitive science. And now some of the debate is about AI. But it's interesting to see things like key value dictionaries being inserted into the neural network systems, external memories, and so forth. They look very much like neural networky ways to do classical symbol manipulation stuff. I think it's really interesting to think about that when you're talking about knowledge injection. Does the answer turn out to be that, yeah, you need key value pairs, maybe you need stacks, and you just kind of rebuild all of the symbol stuff and never acknowledge that actually those were good ideas from a lot of people from before. So that's my opening statement.
Thank you, Gary, and lots more to come. Next is Louis Lam. We're very happy to have you with us. You just landed, I guess, in time for the panel. Louis is a professor of Foundations of Computer Science and AI, as well as Secretary of Innovation, Science and Technology of the state of Rio Grande do Sul, Brazil. He has worked on neuro-symbolic AI for over 20 years, published a seminal monograph titled Neuro-Symbolic Cognitive Reasoning, and co-organized several workshops in this field. He holds a PhD in computer science from Imperial College London. Louis?
Thank you, Gary. Thank you to be here. I'm very glad to be here with Vered, with Partha, Gary, so our many friends over here. Of course, it's a great opportunity. And building on what Gary has just said, neurons and symbols have come to the fore recently. And this is also a consequence of one of the first AI great debates where Gary presented the history of his work and also mentioned that learning and reasoning are, let's say, parts of AI that in cognitive science are studied into a much more specialized foundation, and where one integrates, when one tries to integrate cognitive abilities. And in one of his books, Gary makes the case for hybrid models. He reinforced the case in one of his recent papers in the future of AI. But in a technical sense, to integrate symbols and neurons, or to integrate learning and reasoning, makes perfect sense, because we are here to build richer AI models. We are here to build more robust AI systems. And if one wants to build systems such as large language models, one has to take into account the plethora of possibilities and techniques that are already available for computer scientists. But one has also to consider that if one wants to build AI at scale, AI that shows meaning, AI that shows inferences that are based on solid foundations, one has to build models. And logic offers several tools to build semantics by construction. There is no logical system or a formalized logical system or reasoning system without a formal semantics. And when we are dealing with language models, as some of the very interesting talks before the panel have mentioned, one has to consider as well some possibility of building a richer model. And these richer models come with the price of establishing a formal semantics, and of course, to looking into more detail of what's going on in the reasoning process, not only about what happened at the level of large amount of data, but also one has to think about what's the semantics, what's the model, what's involved in the kind of reasoning that such large language models do these days. I'm just mentioning large language models because they're very popular today, but in the quest for identifying the necessary and the building blocks of AI and how to build systems that evolve automatically based on machine learning, we have to find ways, and we have to work towards effective ways that make AI more trustful. That's one thing that's even in the press these days. And we also have to find the best representations for neuro-symbolic AI, and for systems that allow us to build the principal integration of learning and reasoning. So this is the kind of thing that I hope that we can contribute a little bit in the debate today. Thank you, Gadi.
Thank you, Luis. And we'll definitely go back to large language models in the discussion. Next is Partha Talukdar. Partha is a staff research scientist at Google Research India and an associate professor at the Indian Institute of Science, Bangalore. His recent research includes works in multilingual learning, graph-based learning, automatic knowledge harvesting from web-scale data sets, and temporal information processing. Partha.
Okay. Thanks, Gadi, and other organizers for having me here. It's a great honor to be in the middle of all the distinguished panelists here. So so I have been working in the space of, I guess, like knowledge graphs broadly, of how to build them and how to utilize them in deep models. At least the construction part, kind of like I've been working for more than like 10 years now. So I'm kind of like, already sold on this idea. And like a couple of years back, I gave a talk where like, the thesis was that DL plus KG is greater than DL. So to me, the utility of knowledge graphs and incorporating them into deep learning models and neural networks, I think I'm kind of like pretty convinced that that's kind of like a useful thing to do. And I think there are like uncertainties about like how we might be able to do it. Haitians talk about like the film model is kind of like one approach, but there's some uncertainty. We will kind of like make progress on that. But the bigger question that I worry about is the coverage of these external knowledge sources, and the amount of the world that we want to like cover through them, the sparsities that they have, how useful they end up becoming, and or less useful because of the sparsities that are there, right? Because of the coverage is not that great. So, and that's kind of like becomes more acute as you go beyond, like, say English speaking world into other parts of the world where, like, the sparsity is not only acute in terms of the knowledge graph, but also from the data from which you may want to learn those kind of knowledge graphs and, like, build either manually or through automated methods. So to me, that's kind of like a bigger question, I guess, kind of like how we can reduce the sparsity in these knowledge sources, the external memories, and of course, how we can integrate them into neural models. So, and also another aspect is it's not a one-time process, how also we can keep them updated, especially in a dynamic world, and do that in a scalable way. So kind of like building and maintaining these knowledge graphs in a more scalable way seems like a very important question. And of course, that's in addition to how we might be able to integrate them into neural models. So I'll stop here. Thank you.
So the question of coverage, which has been discussed on knowledge graph, there's also some element of coverage of large neural networks. Is something that I'm sure we'll get back to during the discussion as well. And finally, I'd like to introduce Vered Shwartz. So Vered is an assistant professor of computer science at the University of British Columbia. Her research focuses on natural language processing, computational semantics and pragmatics, and common sense reasoning, which is one of the reasons that we have connected and discussed in the past. This is a fascinating area. Prior to joining UBC, she was a postdoctoral researcher at the Allen Institute for AI and the Paul G. Allen School of Computer Science and Engineering at the University of Washington. Vered.
Thanks, Gadi. So I'm going to split my statement to two parts, one about knowledge and the other one about reasoning. And it's going to focus on language because that's what I work on. So in terms of knowledge, language models are not knowledge bases, but they do capture a lot of word knowledge and common sense reasoning, common sense knowledge. And I see them as a natural continuation of the methods that construct a knowledge base automatically from a corpus. And they do have better coverage than knowledge bases, and they can be used to generate contextualized knowledge on demand. With that said, it's probably not a great idea to rely on them as a source of word knowledge in applications where precision is crucial. And that mostly because, well, first of all, it has been shown that they're not very good at handling negation, which is pretty crucial. And like all other distributional models, they tend to confuse semantically similar but mutually exclusive concepts. Like, for example, if you use Bert to complete the sentence, the mask-colored dove was on the bench or something like that, it just outputs a lot of different colors with similar probabilities. And finally, language models also suffer from reporting bias. If you try to complete a story using GPT-2, it always ends up with someone dying or going to the hospital or something like that. In terms of reasoning, I think that at least in the NLP community, it's probably like that in other machine learning fields. There's kind of an obsession with end-to-end neural networks. Even when we talk about neuro-symbolic methods, we mostly mean embedding knowledge from a knowledge base into a neural network and then letting the entire computation be neural. There are some exceptions like the NL Prologue and some other papers from UCL, the Proofwriter from AI2, and some work on from Lee and Sri Kumar at ACL 2019 on augmenting neural networks with first order logic. And I'm a fan of such models that try to stitch together neural components with symbolic computation. And I think that we should do more of that because it would allow us to do more causal and multi-hop reasoning. But of course, there's a reason that there's little work on that. It's just because language is often too messy for symbolic operations. It is ambiguous and it's underspecified. And even in tasks like NLI, where it seems natural to define constraints such as the more specific entails the more general, but not the other way around. Even then, you can have some default elements that break this constraint. Like if I say banana, then I mostly mean yellow banana because that's a default. And finally, I just want to say that I started doing research when word embeddings became very popular. So I don't have a lot of experience with, I have less experience with purely symbolic methods. But I did gain enough experience with neural models to know what they do well and what they don't do well. And I think that deep learning is a powerful tool, but we need to start treating it as a one tool out of many in our toolbox.
Right. Thank you, Vered. And some of you really opened up threads rather than trying to close them. And we'll go to the more interactive part of the session. And I will ask questions. I will ask one of the panelists, and please try to constrain your answer in 3 minutes. But after that, other panelists are invited to just comment, and you can extend, add the point, or you can disagree, which is always welcome in panels like this. And the first question goes to Gary. There's been a lot of buzz around foundational models recently. However, you were quite critical in a recent essay you had in the gradient.pub. Why is that? You're on mute.
That better, yeah. I think there are two issues. One is I think the name foundation model is really misleading because I don't think that these models do what we want for a foundation of AI. So there's some technical sense in which they are a foundation, just like there's some technical sense in which deep learning is deep, like it's a lot of layers, but it's not conceptually deep. And foundation models aren't a foundation in the sense that you would like to build the rest of your bedrock around them. The last talk was an interesting example of trying to like patch around some of its weaknesses. You know, one of its weaknesses is you can't really count on it to know any particular thing, even after gigabytes or terabytes of training data. So let's put a Band-Aid on that. And there are all kinds of places in which it needs Band-Aids, but you don't want your foundation to be ridden with Band-Aids. That's not the right way to do software engineering. And so I really take exception to the name. And the article talks about that. And the article talks about what might be a better foundation. In terms of having reliability, robustness, having representations like dictionaries, symbolic representations that we can do compositionality over and so forth. So, I mean, maybe it's really one answer, one large answer, which is we can't build the AI we need on systems that aren't fundamentally stable or reliable. If you add more information, you retrain, you don't know what happens. We need something more stable in order to build the rest of what we want to do.
So in the way that you see the limitations, is knowledge injection, the ability of having symbolic knowledge in addition to the neural network, is that a potential path to addressing some of the challenges you're raising?
It's a potential path. I'm not sure it's the right path. So like I'm half 100% in favor and half not, if that makes any sense. So we absolutely need to bring knowledge into our large scale AI systems, in particular ones where reliability matters. If you want to do recommendation engine, then maybe you don't need knowledge and you know, my comments don't apply. But if you want to build a driverless car system you can actually count on, or you want to build a language understanding system that you can have a long-term dialogue with, or you want to build a domestic robot, any of those circumstances, you really need the system to understand the world. And the large language models don't really understand it. So one option is you bring knowledge in. The other option is you bring in knowledge, but you actually get rid of the LLMs, or you use them in some more subsidiary capacity, like you use them to find synonyms and paraphrases, but you don't rest everything on them. They're just sort of like one tool that you use. So, you know, 2 thumbs up for knowledge. Whether we actually want to integrate them with the LLMs, I think that's actually open. The last talk is an example of how you would think about doing that if you were going to, but I'm not sure that's the right answer in the end.
All right. Any comments from the other panelists?
You should have had Sutskever here to, you know, give me a hard time. People here.
Yeah, we don't have a fundamentalist among us.
We can play the fundamentalist, but I'm very bad at it. I come from hybrid world, so I'm very bad at being a fundamentalist.
So maybe continuing this discussion, Partha, with the question to you. If you continue to look at this conversation in the community regarding fundamental models and the aspect of using large models as knowledge bases, from your experience and research, what are the particular aspects in which knowledge injection and use of knowledge graphs provide some significant additional capabilities? What do you think is made possible by utilizing knowledge injection in creating the type of system we look forward, like continuously update, common sense aware, and so on?
Okay.
Yeah, that's a great question. So just some of my own thoughts. So one is around, I think, like the ability to generalize quickly to new situations. For example, if I tell you some who is Bhupen Hazarika, you may not have any idea about what that entity is. But then if I say Bhupen Hazarika was inspired by, let's say, Paul Robson, and if you happen to know Paul Robson, then you know that maybe he is going to be like an artist, right? Because artists kind of influence each other. So that way, if I am able to connect some new entity or new objects to things that I know, I think I can kind of quickly learn a lot about those new entities, which otherwise maybe require lots of instances, and I might be able to derive lots of properties from that other related entity, which might take a long time to maybe learn, and also more number of parameters to kind of represent that. So that's kind of one part that we might be able to learn faster and quicker. The second one is about predictability and easy to fix. And that's kind of more broadly about controllability that you may want to have. That's kind of maybe more important in kind of production environments where you see certain types of errors being made by your model, and you want to kind of fix that. So having a grounding in a knowledge graph, I think is going to give you more control over that kind of debugging and fixing process compared to if you have to just rely on continuously embedded space. And that also connects to the third point about explainability. So if you are able to explain your decisions in a grounded to a knowledge graph, I think that's going to be far more accessible compared to just looking into the black box, and that's kind of a problem that we run into. So I mean, just to give an example, say if I'm working in an education use case where I want to learn about, say, deep learning, and I'm asking the system to give me some recommendations about topics to learn, right? So having some notion of a prerequisite graph, which I can think of as a one particular instance of knowledge graph. And that tells me that okay, you have done maybe some high school level maths. So maybe you know about differentiation, but next will be kind of learning about backpropagation, which is utilizing your knowledge about derivatives. And from there, you could learn other concepts about deep learning. So I think having that kind of a possibility of explaining, even in a recommendation setting, I think that is going to be far more useful if there is a grounding in the form of a knowledge graph. So that's what I would say, maybe quicker learning and explainability and more controllability.
So let me ask you a follow-up question on explainability, and other panelists can chime in as well.
Sure.
I can see, and we're actually utilizing it in our labs as well, that if you use a knowledge graph, if you use a knowledge model that is structured and intelligible, it's easier to convey why a decision has been made. But some of the knowledge still resides within the parametric memory. So how do you address explainability when the knowledge that you're utilizing to reach an outcome is in a way split between knowledge sitting in the parametric memory and knowledge that sits in the intelligible explicit knowledge graph?
Right. So yeah, maybe I'll just take a stab at that first. So I think for that, having this interface layer that Professor Subbarao was also talking about, right? So being able to having this kind of a communication layer with humans, right? That you are able to also ground those communications with respect to some, wherever necessary, with respect to some external knowledge. But it doesn't matter kind of what internally you are doing, as long as you are able to map it back to that a common kind of a shared vocabulary. So that way, maybe kind of the knowledge about the world could be split across multiple sources, some of it external, some of it is internal, but you do have a shared vocabulary to kind of like take input and then also generate output. And my thesis or my intuition is that if that shared vocabulary is also grounded with respect to some common belief system or some external knowledge that we both agree on, then I think that communication is going to be far more effective and swift.
Any of the other members? Explainability, and you heard Partha's answer about a shared vocabulary is the key to have the explainability across knowledge spaces. Any other comments?
Well, depending on the representation, Gadi, that's the point I made about using logic and neural networks. Okay, when you build a logical system, you need to go beyond syntax. You need a model, formal model, and any of these representations, if they are graph models or relational models or some in limited sense graph representation, the first thing that someone comes from a logical background, you always look at what's the model underlying all this work. Okay, when you design a reasoning system, you look for syntax and semantics. When you design a large language model, or you design a popular graph model that these days are widely used, I myself use graph neural networks, you always have to think, what's the semantics underlying all this work? And for instance, if you take relations, or if you take predicates, or if you take relational reasoning, whenever I see a paper with relational on the title, look, what's the model that underlies this work? What's the model that gives support this work? Because when you come from a logical background, you always think about what's the model that underlies this thing. For instance, when you use temporal representations for checking or for verifying your systems at Intel, of course, temporal logics and model checking, they have very sound and a very well-grounded and well-defined semantic model. And when I look at all these models based only on data or on huge amounts of data, as Subaral has mentioned in his talk, I think, well, what's the semantics underlying all this knowledge? Is the semantics based only on this vast amount of data that we collected on the web? That would not be a problem if one could offer a proper model for what's going on in this data gathering, but I have not seen this model so far. So whenever I see any model or any paper with relational on the title, with graph on the title, with meaning on the title, I look, okay, what's the model underlying it?
Gary.
I just wanted to pile on that point. So neural networks are models of a sort, but what a linguist or a logician or a computer programmer means by a model is something different. So in any of the latter three, models are transparently compositional. And so you can reliably compute certain operations over those constituents. And neural networks are a model in the sense that you can represent it on your cluster or something like that, but not in the sense that you can have a constituent that you can reliably use in a component of some other process. So, you know, not everybody is familiar with the logical models that Lewis talks about, but probably everybody here has done some computer programming. And you can think your data structures are part of your model. And you can then reliably manipulate those data structures. Your algorithm is built over those. And that is what is fundamentally lacking here, is a model in that sense of the word.
Thank you. And Vered, question for you. Right now, knowledge injection is typically considered as an auxiliary mechanism to aid the neural network parametric memory. So you have the main show, which is within the neural network, and then you have some aid maybe by knowledge injection. Is this the right way to approach knowledge injection neural network, or is it possible to consider an inversion of it, where we have a large curated or otherwise created knowledge base, on top of which you have a smaller neural network that does some functionality?
Yeah, I think that's definitely the easier way to do that, and you do get some gains on some tasks. And even in this approach where the knowledge aids the neural network, there are various ways to incorporate that knowledge. So I've seen some, like maybe the easiest or the most, I mean, the easiest is if you just, if you use a language model and you just pre-fine tune it on some knowledge base, and then you have this knowledge instilled into the language model, and you just train a standard model later. So that's a very like a soft way to instill that knowledge, and it's probably the easiest way to do that. I've also seen some examples where well, graph embedding is pretty popular, where you have for a given instance, you just retrieve the relevant knowledge and embed it and incorporate that into the input for the network. And I've seen some examples of trying to change the computation, but that's already task dependent. Like I think the example I can think of is where there was some scoring function in a multiple choice task, and then the knowledge that was retrieved from the knowledge base was encoded as constraints for the scoring function. And that requires more work, and that requires task-specific solutions. So I think people tend to do that less. I think there's more of a tendency in the last few years to build models that are that work for more than one task. I mean, the architecture works for more than one task, but the models are trained separately for each data set typically. I do think that it's not necessarily the ideal way, but yeah, I think it's just the easier way, and that's why most of the work is like this.
And maybe asking the other panel members, what would you think about a model in which there's a very large knowledge, structured knowledge that contains most of what is needed, and then you look at the neural network as kind of, Gary called it the subsidiary function. So what is supporting what? Is a neural network a function that sits on the primary value that comes from the knowledge model, or is it other way around, like the way it is today? What are your views on that?
I mean, going back to my opening statement, you don't want your foundation to be something that is uninterpretable, uncomposable. You can't do reasoning over, you can't count on it, and you can't count on updating things moment by moment. Like, why would you make that your master controller? As opposed to saying, well, it has some value, like it can make certain inferences very quickly because it's been highly trained. And so you use it for that. But why would you build your whole architecture around it? I don't understand.
All right.
Just to add to that, Gadi, in another perspective, from a foundational point, we like compositional models in computer science. It also comes from the ability that we need to do to build more complex and complex models from scratch or from simpler models. And also from a technical perspective, when we are building systems, of course, it's much easier, and it's part of the culture of computer science, as Gary mentioned. Anyone who has programmed something in the past needs to compound things, and of course, in order to build larger systems. But here, what I see in terms of the interplay between neural networks and symbolic reasoning is that we need translation mechanisms from one to the other. And another point that strikes me is there are several open problems. Perhaps some of the harder problems that we have in learning are associated with transfer learning. But how can you transfer learning from one domain, say vision, to language or to perception, if you don't know what's the meaning of a learning procedure or a learning mechanism in machine vision, and then you want to use the same procedure or similar procedures to transfer that to language and to other domains. So that's why semantics is so important. How can you transfer the learning procedure if you don't have an explanation for what you have learned, let's say? So this is extremely important. It's very crucial to industry, and also to not only to raise awareness between researchers, but to make AI more trustful for the general public. So in order to build things like effective transfer learning, we first need to know what we are learning. So that's a bigger question.
Yeah, and there's discussion, we just touched on it when we talked about analogy and conceptualization. How do you go to a new space? You have to be able to understand analogous situation and context, and you need to be able to conceptualize so that you can then go down and make new observation in a new field based on what you've learned in other fields. And since you were on the roll, maybe ask you about the difficulties of dealing with structured knowledge. So knowledge injection itself comes with a set of inherent complexities. Curation of trustworthy knowledge sources, reconciliation of knowledge between external sources or external sources in your network, efficient injection or update mechanisms, and there are more. So how do you see those issues getting addressed in the near future? Or are we trading between devil in the deep sea?
Well, I don't know. I think Gary was going to say I got in between here. I don't know. Or can I go on?
You can go first.
Okay. I'm going to oversimplify here, Gary. Knowledge at the moment, of course, is grounded onto vector representations for efficient learning and using matrix computations. It's basically what we do these days. Okay, we try and embed things into vector representation or tensor representations and so on. However, we see that symbols, in a way, or the reasoning system, or anything that we build that has to do with reasoning, I have to say that it's hard to build. Okay, no wonder that you have way less people working on reasoning and on building, let's say, automated theorem provers than we have in any other field of computer science. So it's very hard to build reasoning systems from scratch or to build reasoning systems in general. So the thing here is that I believe that the combination of learning and reasoning also offers an alternative to this, to the problem that you mentioned, that is in some way related to combinatorial explosion or combinatorial reasoning by learning. We have to work towards to try to reduce the number of combinations that we have in any reasoning systems and combinatorial explosion. And for that, we need a proper language. And we should start looking at other languages for knowledge representation and reasoning. For instance, when we are dealing with relational reasoning or predicate reasoning, people start looking at what we have learned in our first logic courses that are predicate logics or relational logics. And but people don't even let's say, reason about the undecidability problem, that when you have full first order reasoning, for instance, it's undecidable, so it's very hard to design algorithms for that, and even more so to learn about relational reasoning. So in a way, what we have been trying to do is to show that there are fragments of several forms of reasoning, such as model reasoning or temporal reasoning, or using some form of model logic that perhaps it's better for the purposes that we have in computer science. For instance, when you work at Intel, you are building systems that are verifying relations between objects in a circuit, and all these relations depend on time. So we should look at other formalized logical systems, such as temporal reasoning, and there is a lot that we can learn from that in order to have more effective representations of the reasoning process. And this is what we have been doing for a long time. And another point that I want to make here is that about 15 years ago, people, let's say, didn't have a very positive view on neural networks. But then we see that science has taught us that we cannot be very let's say, ideological about what we believe in science. We have to prove things, and we have to show that things are effective. Well, the same thing I say about logic. People say, well, logics are out of fashion, logics are not very useful, but when we look at the results that we have in the history of computer science, when we look at the results in program verification, in model checking, on the uses that you make that in critical applications, there are several important things that one can do with logical reasoning and with formalized tools. So that's why I believe too that the combination of learning and reasoning offers a very good alternative to building richer AI systems. So thank you.
So before we have others comment on this, I'm audience and Vasudev. We have time maybe for one or two quick questions from the audience. So if you want to post it in the chat window, and Vasudev, if there's a question that comes up, I'll point to you and you can read it for the panel.
Sure.
All right. So was there any follow-on to what Luis was saying?
I think Lewis said a lot of what I wanted to say, and I'll say it's a good question. I mean, I don't think anybody should labor under the illusion that symbol systems solve stuff by themselves. I mean, the reason that Lewis and I have been interested in neuro-symbolic hybrids, and I know you are and a number of other people on the call, the reason is because we know the symbol systems have a lot of problems on their own. You know, a lot of people sort of half read the book Rebooting AI and say, well, it's a critique of deep learning. But there's a section in there where we're just as vicious to symbol systems and say, for example, you need to deal with partial knowledge, which is one thing Lewis didn't mention, although I'm sure he would agree. You know, there are lots of cases where you could see how to solve these things if you had full knowledge of some representational situation. And what's really interesting about humans is we usually have partial knowledge, and yet we usually, not always, do a credible job of reasoning over partial knowledge. That's another example of things that's, you know, really not well solved on the symbol side. And then there's the whole question of where you get the knowledge from. So there's many, many reasons to try to find something that combines the spirit. And there is no reason to be confident that we already know how to build, you know, AGI or whatever it is. You know, we don't.
Yeah, and I think among the panelists, there is a belief in a neuro-symbolic approach, meaning rather than the argument of which is right, which is perfect, and which is irrelevant, how do we combine the two? And hopefully many of the, much of the audience as well. But we do need to find the right way of combining them. So,
Can I add one sentence there?
Yes, of course.
And challenge an assumption in a sentence that I otherwise agree with, which is the way. I don't think that there's one way. I think it's very task dependent, the right way to combine these bits of knowledge. And the thing that most impresses me about the whole brain imaging literature, which mostly doesn't impress me, is that what you see is that humans are really good at reallocating different bits of the brain very quickly. So you throw somebody in a brain scanner, you give them like a minute's instruction, and then you look across people and everybody is reallocating their brain in a way that's relevant to that task. And, you know, most tasks actually require some symbolic contributions and require at least some, you know, visual or metric contributions and probably some memory contributions. And people, like, in a flash, you know, if I say, you know, this is an unusual chapstick that I happen to have at hand, and now every time you see something that has the same color pattern, you can do that, like 2 seconds, and now you can find other things with that color pattern, and you're reallocating some of your symbol machinery to like represent these two and represent that there's a division, and then you're using some of your perceptual stuff. Yeah, I can throw you in a scanner, and I can throw Vered in a scanner, and you probably do similar things. So that's like many ways of recombining this stuff.
Absolutely. Yeah, and even I think the point of when to use neuro-symbolic, there might be some tasks in which pure neural networks, some pattern identification and so on are perfect. You don't need neuro-symbolic. And as you said, neuro-symbolic is not a solution. It's
if you want to be a bullshitter, GPT-3 is great. So if all you want to do is bloviate, you don't need any symbol stuff.
That's right. Vasudev, a question from the audience?
Yeah, we have one question. I'll read it out. Given that we start using neuro-symbolic systems, how do we evaluate them? Do we then need to update the way we evaluate the baseline models or performance comparison in general?
I think Vered probably has a lot to say about this, but I can jump in.
Yeah, I can start. So I think, I mean, the answer is basically the same unless the data set was constructed somehow using knowledge. Like I can think of one example, which is Common Sense QA that is built using ConceptNet. And so they have the leaderboard, and they're separating models that use ConceptNet versus models that don't use ConceptNet. So it is important just to make sure that you're not exposing some of the knowledge the data set was built on. But in general, it's always good to have baselines that are that have access to the same knowledge or to the same models. So you need to show that you do get the gain from both the neural component and the symbolic component.
I would add that I think that benchmarking is an unsolved problem. That what we've found over and over again is that systems solve the benchmarks in ways that we didn't intend and don't really get at what we want from those benchmarks. Is sort of part A. And part B is, I think, chasing benchmarks takes us away from the conceptual things that need to be solved. Benchmarks are often pitched at the level of a whole architecture that solves some complex task, rather than what are the constituent parts that we might need to build architectures in general. And I think we need to focus more on what are those constituent parts and not worry about the benchmarks that probably we can do like 80% on everything or 85%, but maybe we're not learning anything by doing 85% on the benchmarks when we need some conceptual stuff that really is at the level of like neuro-symbolic translation and integration and so forth. And maybe we need to spend a little time on that before we go back to the benchmarks.
Just to add to that, I basically agree with Gary, but I think that this is probably mostly a problem with discriminative tasks. And I think that in generative tasks, you have less of the models are less prone to being right for the right reason, for the
That's
wrong
right. Multiple
reasons,
choices misled us. And if you just, I agree.
But they're also harder to evaluate, and you can't have the same leaderboards unless you're willing to have human evaluation for all the leaderboard submissions.
And Partha or Lois, you want to add to that?
Yeah, I just want to mention that, I agree with Vered and what Gary said about not getting away from the question for the main point. But for instance, when we are dealing with systems that are built to learn to reason, or systems that are doing solving some or learning to solve some combinatorial problem, of course, the benchmark would be to compare with the purely symbolic or the pure system that solves, so that's the best TSP solver or the best solver that we have for any other problem. That would be the benchmark for classical problems in computer science. For instance, people are trying to build systems, neuro-symbolic systems for satisfiability and other problems, things that have a very large interest in industry. Of course, industry will use these tools if they will perform better or give better guarantees in some way for this kind of problems that we are trying to solve. So there are different ways to evaluate. One is from the reasoning point of view, the other is from the learning point of view. And the other thing is the integrative part. For the integrative part, to me, you first have to show that you have a proper semantics. I'm insisting on this point because back in the 60s, where most of you were not born, people were using the lambda calculus to provide semantics for programming languages. And then Dana Scott, who won a Turing Award in 1976 for his work in computer science, said, look, you are using a language, the lambda calculus, that doesn't even have a model. So he first proposed a model for the lambda calculus, and then the field of programming language semantics was founded. So I believe we're in the same stage. We do not have a model for deep learning at the moment. We're just trying to find one that's a proper model for language models or for the other applications of neurosymbolic models that can contribute towards that.
All right. Go ahead, Partha.
Yeah, so I agree to all the points that are mentioned, but I also want to kind of highlight that if something is not working, then also trying to understand whether there is something wrong with the learning or the reasoning process itself, or because of the partial information that's present when you're utilizing that external knowledge. So again, kind of going back to the coverage question, I think separating these two out would also help in debugging better.
Right. And I'll just add the related, even though not a direct answer to that. I believe that sometime within the coming decade, the way to measure the capabilities of AI systems will be to have them compete against each other in some given set of rules rather than giving them a task. If you think about chess championships, you don't figure out who's the best chess player by somebody smarter than all the chess players giving them a test and see who of them is graded the best, but you ask them to compete with each other. But that might be a few years out. So we're down to the closing statement. And for your closing statements, can you share with us, what do you envision as the most significant advancement you expect in AI in the coming 3 to 5 years? And what role in it, if any, do you see for the integration of knowledge and neural networks? And let's start with Partha.
Yeah, so so one thing I've been kind of like lately working on is multilingual learning. And we have like now 7,000 languages in the world. And like, we cannot get to each one of them one by one. And there is like no resource questions among all of those. Like, there is kind of like high web resource and the long tail of low web resource languages. So it has been kind of like, good to see building kind of like common representations, how we can kind of like do transfer across these languages. And I do expect kind of like, progress in that area. And I mean, I feel that like, having like external knowledge, given the way that language is structured, which is a means for communication, and we have some sort of common understanding, and we only speak the delta with respect to that. So both like, I mean, in order to facilitate this generalization across languages, knowledge graphs and external memories of some form is going to play an important role. So multilinguality is one. The second one that I am hopeful of, and I would like to see also progress in, is in the area of multimodality. So when we are learning, like, building a model of the world, it's not just by reading some text. So we also use all of these other sensory senses, and many of them are also complementary, right? So I mean, if you're trying to learn some sort of like common sense knowledge, maybe that's not going to be written down, and some maybe like, images and videos could be useful. So I think kind of like, progress on the multimodal front. I'm hopeful that we are going to see some progress there. And again, knowledge graphs are going to, I think, play a role there, both in terms of facilitating that, and we might be able to also augment the knowledge graphs with these kind of like, other extractions from other modalities, with some sort of maybe human vetting in the loop.
Thank you, Partha. And actually, some part of your answer on multimodality also answers a question that was on the chat that we didn't get to common sense knowledge, because sometimes some of the common sense knowledge that we have comes from a different modality. You know that cars are driving on the street and not in the sky, not because it's written necessarily, but because you've seen it. So Vered, your closing statement.
Yeah, so I was actually going to say something similar to what Partha said about multimodal representations and learning common sense from other modalities. So I do think, I think it's already something that's becoming more popular lately. But maybe I'll add, sorry, I'll add to that something, it might be somewhat related, but I think that we need to go beyond distributional representations. I think that we keep coming across the same problems. The problems we have with language models being or capturing knowledge in a very fuzzy and inaccurate way is the same problem we had with word embeddings a few years ago. It's true that we've made some progress in that now it's contextualized, which is great. But when we want to extract knowledge about the world or incorporate it into systems, then we need some better representations that don't just learn from guessing the missing word in a context, but that can, just thinking like about extensions to that maybe can learn in which cases it's right to generalize statement, and in which other cases, or like, for example, which sentences are constant facts versus which others are something that could be slightly changed, and you can guess, you can predict a word like a synonym or some mutually exclusive concept that also fits into the context. And again, multimodal can be part of that, complementing the knowledge you can learn from text from other modalities, and then building better representations that have more accurate knowledge about the world.
Thank you. Thank you, Vered. Gary?
I'll give a meta answer, which is is saying in Alcoholics Anonymous, which is recognition is the first step. I think it's taken the field a really long time to recognize that things like large language models or their predecessors are not enough, and that there are other problems to be solved. So I've been complaining about this stuff since my 2001 book, and really even before that, and felt like my complaints were mostly going on deaf ears. And now I see a lot of industry towards trying to do better. I think, for example, a lot of people are thinking about common sense. A lot of people are thinking about knowledge. I don't see the right answers yet, or answers that I feel like are going to carry us to the finish line. But for the first time, I see enough good, really smart minds working on, okay, this isn't really going to solve it. And people are increasingly sharp in their criticisms of GPT-3, which I think first people are just like, wow, I can't believe it, does this or that. People have sharpened the criticisms. They have recognized what problems need to be solved, and that is the first step. And maybe on the 3-year timeline, I'm not that optimistic, but on the 5-year timeline, I think that's enough for people to say, hey, this isn't working. We can't put all our investments in just getting more data. Scale is not, in fact, everything. We need better representational schemes that allow us to interact with knowledge. And if that happens, then I think we can do a lot better than we are now.
Thank you, Gary. And Luis?
Thank you, Gary. I have 3 sayings that I like, and I want to build on what Vered and everyone has said here. And John McCarthy already in 1995 said, if you want to build computer systems or a computer to have general intelligence, the outer structure has to be common sense, knowledge and reasoning. So I believe we are working, or we have, as Gary said, we have more people now that are aware that in order to build common sense systems, we need integrative approaches. It's impossible to build only using deep learning or only using formalized logical systems. We need to work towards better integration. And there is also the same, but not the same, this is a statement by Les Valiant in one of his books, that the distinction between learning and reasoning goes back at least as far as Aristotle. So there are things that people don't realize in science that keep going and going until we have, let's say, some better agreement. And in computer science, what we see these days are, of course, more interest, way more interest from the general public. And I believe that in order to have explainable or interpretable models, we will need to work towards better systems that show some form of common sense reasoning and that have humans in the loop. So in this way, I believe that neuro-symbolic approaches and hybrid approaches, as Gary has defended for a long time, will have a major role to play in the coming years. That's what I expected. I expected to see much more research towards common sense learning and common sense reasoning, but in a well-founded way.
And thank you, Liz. And I think that overall, the message that comes from the panel is that we are in time of transition, and a transition to new approaches, which are synthesizing or integrating approaches, hybrid approaches, as was said, logic models, symbolic knowledge, neural network. So rather than asking, as in the first wave, can humans know everything? Let's just get to them. On the second, can machine learn everything from scratch? What's coming up from this is that the third wave, or whatever is emerging, is going to be synthesizing the strength of all of those to create much better solutions. And with that, I want to thank our wonderful panel, and thank you for all of those who joined. And we are at the beginning of an exciting new chapter. Thank you all.
Awesome. Thanks very much.
Thank you.
Thank you.
Thank you. Thank you so much. Thank you. Bye-bye.
Bye-bye.
Thank you, Gadi.